So just like the sun has an interior, the sun also has an atmosphere. And there are three distinct layers of the sun's atmosphere. The lowest layer of the sun's atmosphere is the photosphere. Photo means light. So this is literally the sphere of light. This is the region where light finally breaks free of all of that matter and begins to travel at the speed of light. So if you were to stare at the sun, which you should not stare at the sun, but if you ignore me and you choose to stare at the sun, you're going to be staring at the photosphere. Now within the photosphere, the higher you go in elevation, so the farther away you go from the surface of the sun, the cooler it becomes. Here is our third lecture quiz question. What type of spectrum do we see from the sun's photosphere? I'm going to give you a hint. The photosphere is a hot gas that is a dense source at the bottom with a cooler gas on top. A continuous spectrum, B, an absorption line spectrum, or C, an emission line spectrum. Go ahead and think about it, and we'll discuss in just a bit. So what type of spectrum do we expect from the photosphere? If it's hot and dense on bottom, then it's probably going to give off a continuous spectrum. But as that continuous spectrum then goes through a layer of cooler gas, the cooler gas is going to absorb some of that light. So the answer is B. We'll actually expect an absorption line spectrum from the photosphere. Here is the actual spectrum of the sun. And notice we have most of the light coming through, but then we definitely have some lines of missing color. This is the absorption spectrum that we get from the sun's photosphere. Now, pictures of the photosphere show that it is bright in the center and appears to become darker as we move towards the edge. This is what is known as limb darkening. The edge of the sun is known as the limb of the sun. So as we go, the center is bright, and as we move to the limb, it becomes darker. The reason that this happens is because the sun does not actually have a solid surface. It looks like the surface is solid, but it's not. Don't even think about landing on it. So what's going on is we're actually looking at different depths. Right here at the center of the sun, as we stare at it, we're looking so deep into the photosphere. Just to give us an even number, let's say 100 kilometers. It's absolutely not actually 100 kilometers. This is just an example to help you understand what's going on. So imagine we see 100 kilometers deep into the sun. That 100 kilometers is going to get us down pretty deep into the sun into a region that is hotter, and because it is hotter, it's going to give off more light. Now, as we transition from the center over to the edge, we're still only able to see that same 100 depth. But because of the curve of the sun, remember the sun is almost a sphere, then over here on the edge, that same 100 kilometers going down does not get us to the same hot region. And because it's not as hot, it doesn't produce as much light, and therefore it appears darker. So the center appears bright and the edges appear darker because it's not actually a solid surface. Now, using very high-resolution images of the photosphere, it appears to be a roiling, boiling sea. Now, these pockets that we see, these are referred to as granules, and it's thought that these actually come from convection. The center part that is bright is where the hot gas is rising, and the edges that are darker are where the cooler gas is then sinking. Well, we can actually use Doppler shift to see if these ideas are correct. Remember that if something is coming towards us, it's going to be blue shifted, and if it's moving away, it's going to be red shifted. Well, as we look at the Doppler shift of these granules on the sun, we see that the blue spots correspond to the hotter, brighter regions, showing that those regions are coming out, and that the cooler edges often correspond with red shift, meaning that they are actually sinking. So it does seem that granules are being produced because of convection. The next layer out, so the very bottom layer is the photosphere, the next layer is the chromosphere. Chromo means color. So this is the sphere of color. The photosphere is so much brighter than the chromosphere that we can't normally see it. In fact, we can only see it during a total solar eclipse. So during the total solar eclipse, the moon blocks the photosphere from view, and then we can see the chromosphere peeking out just a little bit as this kind of pinkish region. And because it's pinkish, it has color, so it is the chromosphere. Now, the chromosphere has an emission line spectrum. Okay, this is because we have a relatively thin gas that is very hot. In fact, the higher you go through the chromosphere, the hotter it becomes. So because of this, it actually produces an emission line spectrum. One of the strongest of these emission lines is the hydrogen lines, because there's lots and lots of hydrogen. And the pattern that we get from hydrogen when you put it all together actually appears pinkish, which is why the chromosphere has this pinkish color to it. Now, as I mentioned already, the higher you go in the chromosphere, the hotter it becomes. Now, this is the opposite trend that we saw in the photosphere. In the photosphere, the higher you go, the cooler it gets. In the chromosphere, the higher you go, the hotter it gets. Now, in the chromosphere, we have these spikes coming up and out. These are referred to as spicules. Now, these spicules are very energetic. They can actually rise to several thousand kilometers tall at a rate of 72,000 kilometers per hour. Okay, so what this means is one of these spikes will go from nothing to several thousand kilometers tall and then back down to nothing in a matter of 15 or so minutes. Okay, these things are highly energetic. Now, these spicules are generally found in hot spots of the chromosphere. What's interesting is that these hot spots in the chromosphere often occur above cooler spots in the photosphere. So the photosphere is cool, and then on top of that we have a hot spot in the chromosphere. This suggests that something is drawing heat from the photosphere up into the chromosphere. Our best guess is that this is part of what the sun's magnetic field is doing, affecting these different layers that we see. The last layer of the sun's atmosphere is the corona. Again, we only really see the corona during a total solar eclipse when the photosphere is blocked from view. The photosphere is so bright, it absolutely outshines the corona. Now, when people first started studying the corona, one of the things that they did was to actually take the spectrum of it, and when they did, they found a pattern in it that they didn't recognize. It didn't match any known elements or molecules. So some people started hypothesizing that there was a new element, the element of the corona. Well, over time, as physicists continue studying atoms and so on, they determined that the pattern we are seeing in the corona was not some new element. It was actually from iron, but it was iron that has had 13 electrons removed. Now, every time you remove an electron from an atom, it takes more energy to remove the next electron from the atom. So the fact that these iron atoms have had 13 electrons removed means that something very energetic is going on. This actually starts to give us an idea of how hot the corona actually is. It is so hot that it provides enough energy to remove 13 electrons from iron. Now, as we look in the corona, we see a similar trend to the chromosphere, where the higher we go, the hotter it becomes. Now, because of the extreme temperature, up to 1 million Kelvin, it is so hot that it's actually producing X-rays. Remember, the hotter something is, the shorter wavelengths the peak becomes. So the corona is actually giving off X-rays. Some of these particles blasting off of the corona can actually go so fast that they actually escape, which is what creates the solar wind. Now, in this image, this is an X-ray image showing us the corona, and you can see that it is not evenly uniform. There are some regions where the corona is actually thinner, and some regions where it's thicker. These dark regions is where it's thinner, and these are referred to as coronal holes, and we believe that it's through these coronal holes that the most material is able to escape, again leading into the solar wind. So the solar wind is this stream of particles and radiation blasting off away from the sun, just beyond the corona. In fact, the corona eventually leads into the solar wind. Well, the Earth's magnetic field actually protects us from the solar wind. The particles of the solar wind are actually charged, and magnetic fields affect charged particles. So this causes a lot of these to actually stream around the Earth. We'll talk a little bit more about the Earth's magnetosphere, which is this protective magnetic bubble around the Earth later on when we talk about the Earth. But some of these solar wind particles actually become trapped within the Earth's magnetic field and follow along the field lines so that they fall into the Earth's atmosphere, interacting at the north and south magnetic poles. When this happens, these particles will actually excite the air, causing the air itself to glow. This is the aurora. The aurora is where the air itself is glowing. Now, the different colors actually correspond to different molecules in the atmosphere. The green is caused by oxygen. So looking at the different colors can actually start to give you an idea of what the atmosphere is made of.